Good. So I see a few of you have seen a small part of his talk before, but there's also another part of it. So this is extending denoising score matching with learned and nonlinear SDEs. So this is like the mandatory slide that I think I've seen 2 or 3 times in other talks already so far, which is to say that deep generative models and especially diffusion models have seen a wide number of cool applications recently, from image generation and making like waffleified like hippos to video generation and solving like Navier-Stokes equations, and also the recent Nobel Prize in chemistry for protein design. So diffusion models are fantastic tools for generating data. And just before the kind of roadmap for the 2 topics, I thought it'd be good just to really like concretize things. So just like how to build a diffusion model. Like a lot of other deep generative models, the main idea here is to learn some sort of push-forward mapping from a simple distribution to photos of anyone know who this is? Someone a little more local and with New York history, a few blocks away. It's Richard Courant. And the idea is to break up this generative modeling problem that would just be like learning a push-forward mapping into a sequence of like intermediate problems to be solved somehow. And there's sort of like a wide array of like papers over the years that have formalized this in different ways recently. And then just concretely, we'd like to model like one variable. We have access to another one. We somehow define these intermediate ones. We want to set up a machine learning problem of some sort so that we can learn to move along the set of random variables and to go from one side to the other. And just because we've already seen a diversity of perspectives on this in the talks yesterday, though they can be made equivalent like 2 slightly different looking ways at the surface that people tend to explain this part, is either that of like starting on one endpoint and integrating like some sort of SDE, or like starting with both endpoints and just sampling variables in the middle one way or another. And then what does this learning to move along mean? It just means that there exist like certain conditional expectations that we can approximate, that once we approximate them, we can plug them into our favorite like ODE or SDE and move along the set of variables. So just to make that a little more concrete. And at a higher level, there's this kind of like a design space of these diffusion models where we have the data distribution we'd like to model. Over on the other side, the sort of like simple distribution we have access to. Which particular way we define the intermediate sequence of densities, and how exactly we go back to generating data. But training diffusion models requires seemingly small choices that can significantly affect results. So just a quick example of what that looks like. Taking this like second approach for how to define these intermediate variables, we could just name a few different choices of these coefficients that mix like data and noise. And for otherwise the same exact code base, same exact architecture, like all that stuff, we have this measure of like image quality that people report in image modeling. And we just see like a wide array of sort of results. 32 to 37 is sort of a big change in this like image quality metric, just like only affected by like these choice of like noising process coefficients. So one question is, what else are we losing by keeping these choices sort of fixed to one kind when we see that like several different choices affect results? And the other part of what we'll talk about in a moment is also like which applications beyond just sampling or generative modeling are we missing due to the limited flexibility in like specifying noising processes in only one way but not another. So this talk is mostly focused on like this part up here. But in general, one could be fascinated to kind of poke at all these like different moving pieces. OK, so for the 2 topics, first is extending these choices of like noising processes from these fixed like alphas and sigmas or fixed SDE we saw to things that you can actually parameterize and learn together with the generative model. And in the second part, we'll be talking about how to use the same sort of objectives that people use for training diffusion models to approximate the scores of like other types of SDEs that are not taken as noising processes for generative models, but that are just interesting in their own right. So for this first part, sticking with this like SDE way that we just saw of specifying these noising processes, the idea is that we have to pick this like noising SDE, so to speak, carefully in a few ways. One of the constraints we already saw is that it has to end up in a given place. And some common choices are like this Ornstein-Uhlenbeck or like variance preserving SDE. This beta t here is just like a simple function of time. People have explored like other choices. So like inspired by some like sampling literature, we could take like, let's say, not just all of our image pixels or cells of the PDE, like discretization of space, but we could like pair all of them, for example, with these extra momentum variables. So like similar in spirit to things like Hamiltonian Monte Carlo. And we can name these sort of like coupled SDEs that like maybe put noise in one coordinate but mix it into the other one. And people have shown that this like has interesting consequences for the quality of generative models too. And looking at these two choices, if you're just getting started with training diffusion models, a natural question is like, does it matter? We saw one example already where it mattered a bit. So here's like a pair of like simple baseline image generation benchmarks, MNIST and CFAR. Bits per dim here is like bits per dimension, which is just a type of standardized negative log likelihood. And we see that we have these two noising processes, like generative models built exactly the same way otherwise, meaning same architectures and learning rates and all that stuff. And we see essentially that one is better on one data set and one is better on the other. So CLD is better on CFAR because lower is better. CLD being this critically damped Langevin dynamics in the second one. And then naturally, if we see two noising processes, and we see that one is better on one data set and one is better on the other, we could naturally ask, well, okay, well, what about like a third data set and maybe another noising process? Or maybe even just for these two data sets, is there a way to just pick some third process that just does better at both data sets? And what I meant by careful choices earlier, there's a few different like algorithmic like frameworks. Yes?
We have a little bit more time. Maybe I can ask the question.
Yeah.
What is the intuition behind these two methods working better on CFAR and I mean, CFAR and MNIST everybody knows in this room, I guess. So what's the intuition of why BP works better on one and CLD on the other one?
Yeah, so there are people in this room that could probably correct me, but I think that if you take like the data, pair it with this extra momentum, so to speak, or velocity variable, integrate this like coupled system, inject noise only in this extra coordinate, and then you look at the marginal distribution, like forget the second coordinate and just see what's happening with the dynamics of the main coordinate, so to speak. I'm pretty sure it gets like smoothed out in some way, or the density path has some more like desirable properties such that the score that you have to match at all the different times changes in a slightly less like drastic way. If anyone else has like other intuition, I know Yuanchi has also worked on this topic. Feel free to speak up if anyone has a thought on it. So I just empirically, as an observer, observe these results. So I think the systematic way would be to like carefully inspect the time derivatives of the densities according to the Fokker-Blank equation and see what's going on, which I have not done carefully. Charles, yeah.
So when I see those numbers, those bits per data, right?
Per dimension.
Per dimension, okay. I have no idea how meaningful the difference is in the quality of the image that's generated. Like, is that something I could spot by eye, or?
Yeah, so I think for like CFAR, something like 3.1 was around the state of art for diffusion models, like around 2021 or 2021 and a half. And then let's say the current state of art. I think it's a really troublesome metric to report because it's also expressed as like an integral over the diffusion loss. And that integral has this property that if you change your numerical tolerance for the minimum time between like 1e-4 and 1e-5, you could completely flip like a bunch of results. Yeah. But let's just say like 2.8 is like the conservative number that is like the state of art right now, let's say. Some people report 2.6, but I'm not so sure. But just in a sense of, let's say, like several years of like the rapid pace of diffusion modeling progress has moved this like log scale number about that much.
Okay.
Does that help a little?
I mean, I think that's on me to do the homework. What would help is if I could actually look at the images that are being generated by the different.
I see. Yeah. Unfortunately, I think because these are so small images, maybe not too much to appreciate from the visual. Also, like with images and likelihoods, like people do have a suspicion that the last amount of bits per dim left to optimize are like not things that are like kind of on the high level perceptually obvious, but still make a big difference in the distribution that you're modeling.
Okay, yeah, that was my question. Great, thank you.
Okay, and so about these careful choices, like we saw that we would like to end up at a given noise distribution so that we can reverse a process. We need to be able to, for reasons that we'll go into in a moment, we need to be able to compute these like transition densities to be able to sample an intermediate noisy state given a data point x0. And then there are different objectives, so one of them is score matching, and it requires this quantity. And so the idea is, can we satisfy these criteria in one parameterization? Here is like a general form for like a linear SDE that perhaps takes the data coordinates, pairs them with some auxiliary variables, puts it all into a big state xt, multiplies it by a time-dependent matrix, and then we have some like diffusion coefficient, either scalar or a matrix in front of a noise. And the idea is whether there's any constraints on these A's and D's that we need to encode to actually get like nice, convenient algorithms. And this is an example from the critically damped Langevin thing. I think for the crowd in this room, there's nothing scary like in these 2 pages, but definitely even I think for us, like a little bit error prone. And the idea is like deriving the transition density for this time t given 0 distribution. And also making sure that it tends either at time 1 or some other arbitrary time, like something simple like a Gaussian. And so kind of what was explored by my collaborators and I in this work was to go through like parameterizations that satisfy the like easy transition kernels and that end at a desired distribution, but are also like parameterizable in a way that's like meaningful to like learn the parameters. So here we just have like 2 auxiliary variables, for example. So we have these parameters that are 3x3 matrices. The D is responsible for mixing noise in. The Q is responsible essentially for like mixing information like among coordinates. So it's a skew-symmetric matrix. And we can show that this parameterization under these 2 matrix constraints spans like all linear diffusion processes that have a stationary distribution. The way to check the stationary distributions of these things is to plug in this SDE into the Fokker-Planck equation and see where it zeroes out. And in short, the idea is to learn these parameter matrices Q and D. There's a few ways to think about what that is. If you're familiar with variational inference, the Q's and D's are variational parameters in an approximate posterior, where the generative model is the diffusion model. And interestingly, even though if you open like the applied SDE type textbooks, the transition densities for these like multivariate processes look a little bit like annoying, but it turns out everything is incredibly amenable to like autodiff and like just computation in PyTorch. You can basically use a few inverses and Cholesky decompositions that are not very expensive because even for high dimensional data, these matrices are just like 2x2 or 3x3. So the transition densities are computable. And the first thing that you might be curious about is just to write down like a random Q and D matrix and just try to optimize the diffusion model. So I just literally put some 1s and -1s in these matrices. And then we get a third process, doesn't have a name, just new. Happens to be better on, about the same as like CLD on CFAR, and then a bit worse on MNIST. And then the idea is because the transition densities of linear SDEs are multivariate Gaussian, they're like reparameterizable, and you can get reparameterization gradients for Q and D, so you can just optimize them in like a score matching loss. And when you do this, again with the same neural networks and learning rates and everything, you get down to about 3.07 for CFAR and 1.28 for MNIST. So this like satisfies this criteria of being about as good or better than the fixed choices. And what else is interesting is if you take the fixed choice of the like variance-preserving diffusion and you instead just make the architecture 3 times bigger, that's about the same gain as changing this noising process. Which is nice, because at the time, this was roughly the difference between like 1 GPU or 2 on the compute setup that I had. So I could run an experiment on 1 GPU. So that concludes the part about just this first part. The next part is like shorter and about a slightly different topic. Any quick questions about the learn noising process? And so looking back at it, I think like there's a conclusion slide at the end. But it's like a really basic aspect that when you pull up software to train a diffusion model for your new like applied problem, it usually has like variance preserving schedule, variance exploding schedule, you know, cosine noise schedule, and there's like 3 or 4 choices. There's sort of a question of like whether that's necessary or maybe the default type of code base should actually just have like a noising process that has learnable parameters for your problem. Okay, and in the second part, moving away from, though there are applications in generative modeling, moving away from like this time reversal thing and wanting just to like sample a distribution, and just considering a basic scenario, like you just want to do score matching for new kinds of SDEs. So one example of this is like we have this like paired variables x and v again, and they interact in some way. And we can see that there's a cube on the x, and so this is like this like nonlinear coupled SDE. And what we'll see is that we can get interesting algorithms just by essentially breaking apart diffusion objectives into like local, time local chunks. And just a refresh, we skipped the details on how exactly to train like this diffusion model earlier. But if you have this noising process and you know the transition density, and if it's linear, then we have a Gaussian transition density. If we know the transition density, we know the score because it's just grad log of a Gaussian. And there's this like classic score matching objective that we plug in. S theta is a model. We do regression, and we approximate the this score at optimum. But if we go back to like this abstract SDE up here, and we pick a nonlinear diffusion, we can still possibly simulate the thing to get samples of like this variable yt at a given time. But then it's not totally clear how to do denoising score matching because we saw we needed the score. And so the score is something we don't know in general. Or even the conditional score of t given 0 is not something we know in general. There's this amazing like Stein's identity, which equates for, I didn't put the conditions here, but if your distribution is not crazy in some way, and doesn't have boundaries, for whatever functions like h, there's an equivalence between, inequality between like the expected dot product of a score and a function and the negation of the expected divergence of that function. So the divergence over there being like the trace of the Jacobian, or there's a negation between the two. So we could take our denoising score matching objective, take the actual conditional score on the right, apply the Stein's identity, and end up with this other objective, which has been known for a while in the machine learning and statistics community. So like implicit score matching objective. For anyone that's ever worked with the implicit score matching objective, is it friendly or desirable in any way? Or has anyone ever worked with it? Yuanchi doesn't like it. That's enough for me because I trust Yuanchi on everything. So just quickly before talking about its caveats, Where these two objectives come from, logically, depends on your community. So if you think about the likelihood perspective, you have a generative model, you have a noising process that gives you a variational distribution, you derive a likelihood bound. You get a likelihood bound that directly features the divergence, and you could possibly use integration by parts or Stein's identity to turn it into denoising score matching. Alternatively, some people start off directly with the time reversal thing, and they see that the reverse SDE has a score in it that they need to approximate, and then they directly go for like regression. So people like start with one or the other and then convert between the two. So the trouble is, for high-dimensional stuff, even though all we need is the trace of the Jacobian, because a trace is not easily expressed as like a vector Jacobian product with just one vector, you essentially like need to both call autograd to compute the divergence, like during the forward pass of your loss function, and possibly like do so many times to get the exact divergence. And so the trick that a lot of people have used is just this like trace estimator with Gaussians. Numerically, you would compute your score model. You would ask Torch to do a vector Jacobian product with the Jacobian of the score model and this noise vector. And then you take a dot product with that same noise vector, and then you average over this. But it turns out to be slow and high variance and unstable to train. So one example is I have a simple 2D data. And then with the same kind of like not very well tuned, but just generic like baseline diffusion code bases, I try to do implicit score matching, and I get this. As opposed to what would be like other explanations. Yeah, so we'll see it in a moment in terms of curves of like the loss functions, but basically it never converges. Please.
But I know that in like other situations, people use the JVP Hutchinson's estimator. They only take like one sample.
Right.
Like, oh, good enough. Did you try doing more?
So people try to do more, but then the problem is to use like let's say even 10 samples. You actually need to do 10 forward and back props through your giant score model, like at every step, basically. Or you could sacrifice your batch size and replicate data points with different noise. OK, so going to this like local insight, excuse the word elbow here, which is just negative of the loss functions we've been talking about. We're just going to quickly, in just a minute or two, see like a way to just simply apply like denoising score matching, like doing something incredibly simple that outperforms optimizing, like outperforms in as measured by implicit score matching, optimizing implicit score matching. And just like one tiny example of where these nonlinear diffusions come from. So for example, if we just had a potential like on a circle, theta here is like the angle of moving around on a circle, we have a pretty simple SDE here that is essentially just running like Langevin with this potential. It has a drift that's nonlinear because the derivative of u with respect to theta for that potential is a nonlinear function. This is what it looks like. But already, even with this simple like 1D example, the time derivative of the density is this like not generically solvable thing for different b functions. So just a cute example of where these kinds of things come from. More generally, in the Riemannian like score matching literature, there's like tons of these nonlinear drifts everywhere. And just like if someone locked you in a room and tried to ask you to make like denoising score matching work, one thing you might come up with is something like simple, like just like Taylor expanding. We know that nonlinearity causes a problem. We know that Taylor expansions make things locally linear. Why not just literally Taylor expand the nonlinear drift into a linear one? And once we do this, we get a locally linear transition kernel, which has known Gaussian transition. So the idea is to break apart the diffusion integral into pieces, Taylor expand locally, and do Gaussian denoising score matching. It sounds simple, but there's already like interesting design choices. So here, like, there's different types of Taylor expansions you can pick for functions of 2 arguments, whether you expand around the target time or the time you're at. Also, how to even pick these like pairs of times, S and T, along the diffusion trajectory. An example of something that's helpful is the diffusions evolve like in a way that isn't like equal in all equal time intervals. So you might want to like pick S and T pairs that preserve a certain spacing of like the integral of the diffusion coefficient. Here's an example of optimizing this like localized denoising score matching. And some other applications of where this might come up in generative models is like picking. Up here, I have a slightly more generic form of this like parameterization we saw that now covers distributions that are proportional to exp of negative of this like u function. And so the SDE up top has stationary distribution proportional to that. And so the moment we pick grad u that is not a linear function, we get SDEs that are nonlinear and have non-Gaussian stationary distributions. So one example is like wanting to pick a diffusion that ends at like log of a gamma or at a student t or logistic. And if we, I think this is like either probably CFAR with like a smaller model than we were looking at. You could pick these different nonlinear SDEs that end at either a logistic or a mixture of Gaussians. And you can optimize either the implicit score matching or this local one. You can ignore the row that says PW. And we essentially see this thing where even though we're measuring in implicit score matching as an objective metric, we optimize it better with the localized DSM rather than the ISM. Another example here is like this active swimmers. This is like this nonlinear system. It's an interacting particle system where each particle kind of moves around on its own, but also like repels or attracts each other. And then the particles kind of get stuck in these traffic jams that make like for possibly interesting materials. What we have here is like different time slices. So this is later moving down. And this is like integrating the ground truth SDE. This is learning its score with like this local denoising score matching, and then just integrating forward. And then this is like what you get with implicit score matching, where the green stars essentially mean that the trajectory has like diverged. And we can basically see that the variance of the samples generated by the system that was trained with ISM also just goes off. And so with those two things, this like framework of thinking about how to work with like a wider set of, so to speak, noising processes, whether they are things we're optimizing to do generative modeling, or whether they're SDEs that are given to us just because we want to study a system. Once you know the score of some SDE that someone gives you, you can also compute other interesting quantities like its entropy change over time. Generalizing both of these things allows us to like automate computation, use learning in places where otherwise we would have some sort of fixed choice or some sort of bad algorithm. Improve performance in generative modeling to match that of larger models, and also allow us to do score matching for nonlinear SDEs. And so a lot of these applications that we saw here are like somewhat toy, but I hope especially that this like last part can enable people to study like interesting new systems with score matching as an alternative to what you would otherwise have to do, which is like somehow numerically solve like the Fokker-Planck equation, like to study time-varying densities. Yeah, thanks. Collaborators Rajesh and Raghav on this sort of stuff, and I had a few other like small results I didn't talk about independently, but that were part of a setup that has to do with this other work. One nice thing is like working with like a mix of like computer vision and applied mathematicians. It's really fun. So yeah, thanks so much. Yes.
A minute question. So why can't we do vector Jacobian products with traces of matrices?
I think I guess to get a trace, wouldn't you have to do the like first basis element vector Jacobian product and then add it to the vector Jacobian product with the second basis element and then the third one? So you just have to.
So the trace is a linear operation. Mm-hmm. So you can pass the derivative inside of the trace, and then you just have a vector times a sum of.
Sorry, can you say that again?
You don't have the Jacobi. You don't want to have a computer.
Oh, yeah. Sorry. So this is
That's what I'm saying. You don't need to compute it explicitly.
Yeah, you can do JVPs.
Yeah, exactly. But your
I think
statement
you
was
need-
that we can't do it with the...
I think you need to do number of dimensions Jacobian vector products. I think.
Correct.
Yeah.
Yes. Oh, and that's
Which is
already,
just slow,
that's
or-
already
yeah,
prohibited.
yeah.
Okay. Okay.
Yeah, one thing that's nice about the localization is like you think about it and you're like, it's just some Taylor expansion thing or whatever. But then it ends up making like the difference between a kind of very clunky or very simple algorithm for roughly like the same or better results. And I think that these things are hiding everywhere in these setups. So I think there's a lot more places to find like simple tricks for training these things. If there are no more questions. Yeah.
So at the second part, you kind of give this perspective of you want to linearize a nonlinear SDE and you Taylor expand. But could you alternatively just maybe first like try to learn something like a piecewise linear? And so, for example, in the simple example you show of these blobs of data, could it first conditional on like different condition, and then instead of learning this unconditional sort of density, you like condition on different condition, but then the conditional score, the conditional density is linear. Or like in some sense, you can interpret it as sort of learning a mixture of Gaussian. Like,
Yeah, I think like some of the interpolant stuff tacitly does this.
Yeah,
So
yeah.
what it does is it still names like noising processes whose conditional scores you can compute.
yes.
But once you take a conditional expectation, you end up with some totally possibly nonlinear drift.
Right.
So yeah, you can definitely do that if you are like, I want to design new nonlinear drifts implicitly by picking interpolants and non-Gaussian base distributions.
I see.
But then I think where it would be hard is the other way around, where you're not doing generative modeling, but someone just hands you a very, very specific nonlinear SDE.
Right.
And then you'd have to think backwards, like how can I pick a base distribution and a simple noising process whose conditional score can compute such that its conditional expectation is
I see.
the given nonlinear drift that someone gave me.
I see.
Which
But
is
then the
challenging to reverse engineer.
But then the Taylor expand, then you can just apply
Yeah.
it to any. Got
But
it.
I think you're right. There are other ways for generative modeling where you get to choose the nonlinear SDE to construct them. You can also use like invertible functions, which can be highly nonlinear but still have known density because of like normalizing flows. So you can either like implicitly define nonlinear drifts, explicitly define them as the drifts of push forward like densities of invertible functions. There's a few ways to construct them.
Thank you.
Okay, let's thank the speaker again.